Good morning, everyone. Apologies I couldn't be there, but that doesn't mean you don't have to hear from me. You still get to hear me explain math. Some of you are like, yeah, and the rest of you are like, come on. Day off, please. Apologies. Math keeps going. I apologize, but I'm not actually sorry. I'm pretty glad to be here, even if it is only remotely. It is slightly frustrating because I've lost count of how many times I've said something far too stupid and had to restart this recording. The benefit is that I decided that asking questions and then waiting for responses was not going to help, so you just get me continually talking about mathematics. So it's very likely that you've seen the product rule and the quotient rule, and in fact it's very hopeful that you have, given I'm assuming that you have. In which case, you remember that the product rule says you take the first function and you take its derivative. So the derivative of this is just 1. You multiply it by the second one, 1 times the square root of x, and you add to it the first one times the derivative of the second one, which is 1 over 2 square root x, and I multiplied it through. And we get this, and then potentially you do a whole bunch of simplifying and you kind of regret that you now have to do the algebra on this. But the calculus wasn't, hopefully, horribly, fiendishly difficult. And there are a lot of ways people will typically remember this, either first derivative second, second derivative first, or right d left, left d right, or I've even heard LDR, RDL. There's another way that I was shown, which was created by a bunch of math ed, like their job is studying how people learn mathematics and ways to better help people remember it. I mean, I want to describe them as math ed people, but that's a broad category that doesn't necessarily encapsulate all that they do. And they came up with this method, and I cannot count the number of times I've shown this to students, and then all over their homework as I'm grading it later, I see, oh, yep, they use this. This is a helpful thing that helps them remember it and helps them see the process. So we're going to do the same question we just did, x plus 7 times square root of x. Let's change it so it's not exactly the same. Let's make it an x cubed. It would be exactly the same. I just don't want the same numbers up there so you don't get the exact same answer. You get an answer very similar to this. Most of you can look at this and already see what you would need to change. But regardless, we're going to go over it with this method. So this method, it's the exact same product rule that you know and are coming to love, but it's a different way of thinking about it, where around my function that has a product, you'll notice, product rule does apply. We do have square root of x times another function. We're just going to draw a giant diamond. And we're going to pretend that I have vaguely straight lines and whatnot, but it doesn't actually matter. And here's what we're going to do. We're going to go around the diamond, and we're going to keep, differentiate. We're going to add then that we keep, and we differentiate. Okay, so what does that look like? Well, keep x cubed plus 7, differentiate square root of x. That's 1 over 2 square root x. Plus, keep square root x. Why am I making a fraction? I'm keeping everything. Keep the square root of x, differentiate x cubed plus 7. Well, that's 3x squared. And we stick that in a box, and we're nice and happy. And I'm making sure that the plus sign, you can't see the plus sign at all. That's kind of frustrating. So it's keep, differentiate, plus, keep, differentiate. And as you do this more and more, you would stop writing the keep, the differentiate, and the plus sign. And you would just remember, oh yeah, I keep this one, then I differentiate, then I add, then I keep that one, and I differentiate this one. I'm going in a giant circle. And I would ask, let's think about this. Does it matter if I were to have kept that one, differentiated this one, then added over here, then kept this one and differentiated that one? Would that make a difference? I would love to pause and leave time for you all to answer, but I have no clue if I can't respond to your responses, so we're just not going to deal with that. We're not going to make this a Dora the Explorer thing. Though you are welcome to respond, and Rebecca will pause and answer questions. I don't know how well that will go, given I don't think you've seen this method either. But that's okay. I cannot count the number of students' homework assignments I've graded after teaching them this, where I just see a diamond drawn around a product. It has a few benefits, not the least of which is when I was grading homework, if a student didn't use the product rule properly, I could just draw a diamond around it and be like, well, that's what you missed. That's the step you forgot. Now, we don't have paper homework. That's not super applicable to us. But I want you to ask yourselves, is this something that could help me? Is this something that I want to put into my easy to grab mathematical toolbox of stuff I always have on me? Or is it something I'm going to put in the larger woodshed of mathematical tools that I have largely forgotten about? In there lives stuff like most trig identities and completing the square. But in the toolbox that we always have, it's cosine squared plus sine squared equals 1. That's a pretty important trig identity. Where do I want it to live? Be asking yourself that. For some people, this I draw this shape and the shape guides me through it is an immensely helpful tool. And for others, they're like, I don't need it. Lefty right, righty left, that was good enough for me. Derivative of the first times the second plus derivative of the second times the first, that's good enough. LDR, RDL. I'll be honest, I don't use this one. But if it's helpful to you, then you should use it. Because it doesn't matter what helps other people if it's helping you, right? Especially with math. The end goal is that we're understanding this concept, and whatever tool it takes to help us understand it is a good step in the right direction. Okay, now let's make sure we can actually see the quotient one, as we now leave friendly product rule space and go to just as friendly quotient rule space. The quotient rule, it's nice and it's not. It's nice because there is a simple rule and it's not ridiculously complicated. It's not because quotients aren't. Right, like when we were learning to multiply, multiplication was a doable thing. It took a few steps, but we could do it. And when we were learning to divide, how many people hated long division? I did. How many people feel like they only vaguely remember how to do long division? That's me most days. I can still do it. I'm fine at it, but it takes a moment. Okay, what's the next step? I've got to think through it. Division is the opposite of multiplication, and when we're doing things that are the opposites of stuff, it's more complicated. And we've talked about that quite a bit. Now, okay, 17x squared over negative e to the x. If I want the derivative of this, well, I've already told you we need a quotient rule, but we've got a giant divides by, so it would make sense if we needed a quotient, especially since on top, 17x squared, that's a function. On the bottom, minus e to the x, that's a different function. Amazing. Now we get to deal with multiple functions. And then there's quite a few ways people will remember this, typically. So I've heard LDH minus HDL all over L squared. Now L stands for low, H stands for high, so you'll also hear quite a lot low D high minus high D low all over low squared. There's a rhyme, someone turned it into a song. I don't know the song, don't ask. I just know it exists. Derivative of the bottom times derivative of the top minus top times derivative of the bottom all over bottom squared. That one's more complicated. It's never helped me to remember it, but that's one that people will use. Okay, can I just draw a diamond around this? I mean, there's two stuff in there. There's the top and the bottom, so maybe we think a diamond like this would be nice and helpful. But you know, if I had a diamond like that, it would have a real hard time balancing. Actually, we're in my office, so I can use objects to demonstrate. It would have a real hard time balancing on a point. Just gonna kind of fall. So instead of just making it a point on the base, let's actually give it a flat base. And as you might imagine, that has more effect than me just saying, hey, wouldn't it be nice if it wasn't a point on the bottom? And you'd be right. So here's how the Pentagon rule, I guess. No one calls it that. But the Pentagon rule works. You're going to keep, and then you go around the circle again, differentiate, minus, keep, differentiate, divided by, and then you could draw a square, divided by square. I tend to just write the number 2 to remind us, hey, it's on the bottom, and we're going to square it. We're going to square the bottom. Following this through, okay, so we keep minus e to the x. We then differentiate 17x squared. That is 2 times 17, which is 34, times x. That's the derivative of 17x squared. 34x. Okay, we've kept, we've differentiated. Now we minus. Now we keep 17x squared. We differentiate, minus e to the x. Derivatives ignore constants, so that minus sign just stays. And what's the derivative of e to the x? It's one of the really cool functions whose derivative is itself. In fact, all functions that do have their own derivative as themselves are your favorite number times e to the x. So I've mentioned before 0 is like an exception, but 0 is also 0 times e to the x, so it isn't actually an exception to that rule. I haven't mentioned it in this class, I've mentioned it in other places. Which makes it super relevant to you, doesn't it? Derivative of negative e to the x, we've been talking about it for like 30 seconds. So minus e to the x. Cool. Oh, wait. This bottom line that I said I wasn't just doing for artistic purposes, yeah, that's going to be useful. We divide, bottom line. Fraction bar is a fancy name. Anyone want to guess it? I can't hear you if you do. Vinculum, which is also the overline in a radical. That line here, that thing. Anyway, giant fraction bar, and what goes under the fraction? Bottom squared. Minus e to the x. Quantity squared. And we could do some simplifying if we want. For example, I see this negative and that negative are going to cancel into a positive. This negative is being squared, so what do we expect it's going to do? It's going to disappear. This will stay squared. It's e to the x to the 2. Maybe we could factor out an e to the x from everything and cancel it with one of the 2 in the bottom. But are we done with taking the derivative? That's the question we should ask ourselves right now. Have we taken the derivative? Before we move on to algebra land, yeah, we applied the quotient rule. Low, d high, minus high, d low, all over low squared. Everything after this that we might conceivably have to do is algebra. This was the calculus part. It would be really nasty to have had to do this one with the limit definition of a derivative, wouldn't it have been? Wouldn't it have been? Amazing grammar. It's not technically wrong, it's just a strange formation of a sentence. It is conceivably possible to do this with the limit definition of a derivative, but no one wants to. That's why we have these rules, the quotient rule and the product rule. Let me try and make it so you can kind of vaguely see both of them at the same time, if I'm not in the way. These are things that we're going to get to the point where we just see a derivative and we're like, I can take that derivative. I understand this, I can do that. We're building up to that. Within a few weeks, we're going to be able to take the derivative of pretty much every function you see for the rest of your life. And then we're going to spend the rest of this class saying, okay, now that I have this really powerful tool of the derivative, which measures slope, it measures rates of change. How can I use that? Now that I can do that on anything I want, what does that unlock? What abilities do I get from that? That's really all I have, and I'm going to leave you to ask all your homework questions to Rebecca, who is more than ready to help. Again, I'm sorry that I wasn't able to be there. For those interested, because I know this class and I know there will be a few people interested, why is this the product rule? Why do we know it works? Why does the quotient rule work? Power rule justification, sum rule, and constant multiple rule. How do we know all those work? I have provided some ideas of proofs using the limit definition of a derivative on the boards around the class, unless I forgot, which I don't think I did. Time will tell. Those are for those interested, and if you're not interested in it, well, it's nice and artistic-ish, scary math on the walls around you. It's about what you expect in a calculus class. Best of luck. You're all going to do amazing. I hope the test went well. You got this.